Very interesting. Well, I mean, I have lots more questions, but I feel like I shouldn't get too deep into the mathematics. I'll have to read more into that, of course. One question that I do want to kind of pose is we've talked a little bit about fidelity and parsimony in theories, and so in terms of there's a sense in which I like to think of the progress of science is not quite like a pyramid, but more like a raft, right? So in the sense that all of these pieces are woven together in some sort of fashion, and if it floats, then it's great. And if there's a problem, then you replace a piece and you put a new one in. So to help kind of put this concept in context, I suppose I have two questions. So one, are there any current theories that are well established that we're using, say anything from Newtonian gravity to F equals ma, that would come out as an approximation of quantized inertia, and if that makes sense. So yeah, maybe I'll start with that one.
Yes. So quantized inertia predicts that Newton's first law is not quite right, for example, because it predicts that there is a minimum acceleration in nature. Quantized inertia predicts that there's this minimum acceleration in nature, which is extremely small. It's about 10 to the minus 10 meters per second. But it means the reason for that is because if you, in the theory, if you accelerate less than that, the unreal waves you see are larger than the observable universe, and that can't be allowed. So that straight away violates Newton's first law, but only very slightly. It's a very tiny acceleration. But the other interesting thing about that is that it's the same size as the observed cosmic acceleration. So it predicts that.
Interesting. Yeah, we won't get into accelerating universes, but that's very interesting.
There's a lot of energy required to do that, and they never discuss where that energy comes from. But I'm saying it's coming from information.
So let's probe that for a moment, if that's okay. There's a sense in which if we can estimate the size of the observable universe, so there's all these fun examples that one deals with in a statistical mechanics course, if you look at it from a Bayesian perspective, on tapes that you can mark tapes of information, and then you erase that information, and then you can mark that tape again. So I just want to clarify that if I understand it correctly, what you're suggesting is that once you've erased information, you might be able to derive some energy, but does that preclude that region of space, let's say, from storing information in the future?
Yes, well, that's an interesting question. Yeah, somebody else asked me that, and I don't know the answer. So they were asking, would there be sort of ghost information which remains that you can recover at a later time? It's a very interesting.
Yes. So I mean, I think that's also a very interesting question, but maybe I'm asking something slightly different, which is it the equivalent of burning a piece of paper so I can never write on it again, or is it the equivalent of erasing something on my iPad so I can scribble on the same iPad again all I like?
Well, it must be the fact that the information can return, because obviously when we I'm just trying to think of an example. Well, for example, if you could hide the sun, the theory predicts that you could hide the sun. If you spin very rapidly, if you spin very rapidly, then this horizon will come close enough to hide the sun. So presumably then you would not see the gravitational force coming from the sun, because you would have no way to know it was there.
Interesting.
So I published a paper on that.
Yeah.
But then you would have to allow that when the acceleration reduces again, the sun will return.
Interesting. Okay. Right. So there's a masking effect. Okay, I mean, two more questions then. This is fascinating. So let's see. So on the other side, then, if we're saying that information can provide you energy when you erase it, does it cost energy under the theory's parameters to generate information?
Generate information. Yes, and I suppose that would apply to the edge of the cosmos, which is continually generating information. So over time, we're seeing more and more of the universe because the cosmic edge spreads out.
Mm.
So
So
I
then,
think that's what you're saying.
so is that then the suggestion that as the universe expands into whatever it is, although I dislike that statement for lots of reasons, but then there's information being absorbed from the outside. Is that the notion? Or is the notion that there is a finite universe or infinite universe, doesn't matter, and as the boundary that we can perceive expands, more information becoming available to us?
Yes, that's right. I'm just using it to as you kind of wanted an example of that. So that's an example of a process that's doing that.
Mm-hmm. And is there a way to estimate, maybe, I mean, in the same way that we can estimate the size of the universe? I mean, it's a hard thing to estimate, but you could do it. Is your sense in which we could estimate the total amount of information contained? Again, a classic statistical mechanics problem, but I think maybe in this theory it would be more easy to explain. I'm not sure.
Yes, several people are working on that sort of thing at the moment. There are several ways to do it. I mean, you could look at the surface area of the universe and count how many Planck areas there are. And that would be one way of measuring how much information can be stored on that surface.
Mm-hmm.
You can also, you can also calculate the mass of the universe from its size using quantized inertia.
Mm-hmm.
You can get the mass that way.
Right.
Easily. And the mass is going up. According to the theory, the mass would slowly increase.
And what would allow for that? I mean, what is providing the energy for that increase in mass?
So the way I did it was I treated the cosmos like a black hole and calculated the Hawking temperature of it.
Okay.
And then calculated the wavelength of Hawking radiation that's coming off.
Mm-hmm.
And assuming that the Hawking radiation coming off, presumably on the outside, is balanced by the Hawking radiation has to emit inwardly, and stipulating that it has to fit within the volume, so you can't have a wavelength that's longer than the scale of the cosmos. That predicts a mass for the cosmos, which is 10 to the 52 kilograms, which is exactly what they see. Well, of course, what they see has a big error bar on it, but it's within agreement with that value.
Right. So yeah, that's very interesting way of calculating it. So I guess, but the question might be more so if we have a fixed mass of the universe. You suggested, I think maybe I misheard, but I'm not sure, but it sounded like you were suggesting that the mass of the universe is increasing. And yes. So if it is, and there's an energy equilibrium, as you're suggesting, between radiation coming in and radiation coming out, then where's the energy for an increase in mass?
Well, I suppose it's coming from the it seems to be the opposite side. Where's the energy coming from? So I suppose you're generating information. Well, I think I'll have to think about that one. Sorry.
Sure. Yeah, I'd be curious. But absolutely.
Yeah, I've never thought about that.
Well, we can continue the interview, Mike, and if it does occur to you while we're talking, let us know, and we'll cut that in.
Okay.
Yeah.
Well, fascinating theory for sure, Mike, and so many things to discuss. But maybe we should leave it with this concept of energy balance. And I think there's a lot of interesting things about why inertia is certainly an interesting concept. And maybe the last question I'll pose for now, and then we should certainly pick up the conversation, is whether you think the theory might have any impact on first energy conservation, and maybe this is part of the question that we were discussing before, and maybe we should come back to it another time. And then also I'm curious about momentum conservation, because it feels like that's something that's going to very directly be impacted by a new theory of inertia, in the sense that dp dt is normally known as, and I'm not using p as power, I'm using p as momentum, but dp dt is your force, right? So how would those two things be affected by this theory?
Okay. So if I go to momentum, probably the easiest one to talk about. So how can I explain this? You can do it with Heisenberg's uncertainty principle.
Okay.
So you've got dp times dx is supposed to be a h bar over 2.
Right.
So if you imagine an object accelerating in one direction, it will see this horizon behind it. And if, and this is part of the theory, you take dx, the uncertainty in position, to be the difference from the accelerating object to the horizon, then you'll see that behind it, dx is smaller, and therefore dp has to be larger. Because dp is h bar over dx. So this means that from a statistical quantum mechanical point of view, there'll be more chance that the momentum will, the quantum jitter will push it back against its acceleration. So this is another way of seeing the mechanism from Heisenberg's uncertainty principle.
Interesting. So you're suggesting then that there's an imbalance in the stochastic fluctuations that is suggesting that one side is favored over the other.
Yes, that's right. So that is directly mixing quantum mechanics and relativity, because I'm getting the dx from relativity to horizons. But of course, Heisenberg's principle itself is from quantum mechanics.
The perennial quantum gravity problem. Very, very interesting. Okay. And I mean, I think that's very interesting, because there's a lot we can say about information transfer across both relativity and quantum mechanics. But on the other side, I mean, how would you? I mean, how is it fair to say? I'm presuming it is. So maybe this is a dumb question, but is it fair to say then that your standard theories of momentum conservation, i.e., one billiard ball colliding with another billiard ball, are those things that either in the direct theory or in an approximation of the theory could be explained?
I think that's an approximation. I don't think momentum conservation survives in the theory, but at all the accelerations we know, terrestrial accelerations, quite high ones, the difference is minuscule. It's very small. But you can only see the changes at the edges of galaxies in deep space, at the edge of the cosmos, where everything is accelerating very slowly. Or if you you can see it more directly if you shrink the cosmos. So you have one of these cavities, these metal cavities, and have things accelerating in them so fast that they see the cavity as the cosmic horizon.
Mm-hmm. Fantastic. Well, I mean, I think I'm looking forward to diving deeper. I guess I'm going to pose this now as a question to everyone on behalf of, well, particularly to you, but to kind of follow up on some of the things that we've talked about in terms of theories, right? So I think it's really, really fascinating work, Mike. So thank you for talking about it.
Thank you.
I guess two closing questions that you should totally feel free to say. If you don't want to do it, we'll cut it. But two closing questions that I'd be curious for your take on. So one, in the sense that science is a continuous process of trying to disprove ourselves, what might be some evidence that would suggest that the theory needs revision? And two, I'm just curious for your confidence in this. As we await more experimental evidence and data, do you think it's a 99% theory, an 80% theory? I'm just curious.
Okay. So what could be wrong with it? I'm very sure that there are a lot of things wrong with it. Mm-hmm. I tend to approach things from quite a simple. I tend to simplify to the extreme.
Right.
And for example, a paper has been published recently that shows that some of my assumptions are approximations. So I'm sure if other people got involved, they would improve the theory a lot. I suppose the main counterexample that's used by other people is a bullet cluster, which is supposed to be evidence for dark matter. But at some point, I'm going to have to deal with that. Yeah. And I think I can explain it with quantized inertia, because quantized inertia predicts that if you have an object that's spinning, it will appear to have more gravitational attraction along the axis. This is because the acceleration is lower right along the axis, because that's just the way it works. So you would get something like the bullet cluster. It looks very much like it's spinning. And the extra mass that's implied is at the ends, sort of along the axis. But I need to model it properly. And the other one about my confidence, I'm completely confident about it on a galactic scale. And the reason for that is the fact that the galactic behavior of galaxies changes at exactly the radius that the theory predicts it will change. And I don't think there's any other way that could be predicted. So you see, at this particular radius, the unruh waves become as long as a cosmos, and then the new effects begin. That's very clear. The difficulty would be bringing it down to Earth in the lab. But since I'm very confident about it in space, I don't see any reason why it shouldn't apply on the Earth as well.
Fascinating. Well, thank you for saying that. And I'm hoping we'll get some experimental results in the near future. But thank you once again.
Yeah, thanks.
So, Mike, it occurs to me you're talking a lot about how your theory applies at the galactic scale, at the nanoscale, and it has mechanical theoretical implications, and it has cosmological implications. Is it possible that quantized inertia can be a unifying theory to unify the great theories of physics that are not just have gaps, but they sometimes contradict each other?
Yes, indeed it does. So as you know, there are two main theories in physics: quantum mechanics and relativity, and quantized inertia combines both of them, because the horizons come from relativity, and the unruh radiation comes from quantum mechanics. So it does sort of ram the two theories together in that way. So I haven't worked out all the ramifications of that.